Part 2 of this section talks about piecewise functions. We've dealt with these before in Algebra 2. Piecewise is also another way of talking about a split function. Those are the graphs that kind of look like this, where you might have a line coming up, you might have a curve, then you might have another line, or maybe a horizontal piece or something. They're pieces of functions joined together, and the way that we express them is in terms of domain. We say that maybe this is one part, and then this is another part, and this is another part, and all of them have their own separate domain. So, getting rid of that, we're going to say that they are functions containing multiple parts, functions with multiple parts, each with a unique domain. I'm even going to say a unique non-overlapping domain. That's an important thing right there, that they cannot be overlapping. Overlapping domain means it's not a function, which is a contradiction. So let's not contradict ourselves and keep it that way. Little few things before we get going. We have multiple types of polynomials. This is reviewed too, but any polynomial that looks like f of x is equal to something times x plus another something, like, oh, I don't know, mx plus b. But something that can look like that, that is linear. That's a line. Something that's f of x is equal to this, something x squared plus another something times x plus another something. That is quadratic, which is the shape of a parabola. So linear, slant, something like that. Something like this, f of x is equal to c, or b, or a, whatever. That's not a variable, that's a constant. It's also a line, but it's a horizontal line. And we have other shapes too, like I could say f of x is equal to radical x, but you know, that's a square root, or we could say a radical. And that looks something like this, a half of a sideways parabola. Those are some basic shapes. There are some other ones, but we're going to graph them just as best we can when it comes time to graphing. Number 1 is not requiring you to graph, it's just saying plug it into the function. So, f of 4. 4 is an x value. The rules of this function, f of x, says that it's 6x minus 1 if that's true. It's x cubed plus 4 if this is true, and it's 112 if this is true. Funny thing about this too, the domain here is in set notation, not in interval notation. That's just something to keep in mind. So we're going to say we're going to plug 4 in, but the question is, which one do we plug it in? Do we plug in yellow highlight? Do we plug it in blue highlight? Or do we plug it in green highlight? Well, 4 satisfies one of these conditions, either this, this, or this. And if we look at where 4 falls, it actually falls in between 4 and 7, including right there. So we're going to take 4 and plug it into that row. We're going to plug it into 4 cubed plus 4. 4 cubed is 64. 64 plus 4 is 68. Number B, or letter B, if we have negative 7, that is going to be where? That is, it's looking, it can't find anything. If it can't find anywhere to go, it comes right back and we say it is undefined. Not defined by that function. Okay, let's move right along. We have f of 0. f of 0. f of 0 says to do, take 0. Let's do this part first. We're going to take that, check it against, and it falls right there. So that's going to be, I'm still going to write the outer f, but the inner one's the one we're dealing with. F of 0 is to do 6 times 0 and then minus 1. Okay, 6 times 0 minus 1 is negative 1. So then we're left with f of negative 1. So I'm just following order of operations. I did this part first. F of 0 was negative 1. And now I'm going to do f of negative 1. Let's go back up to the function. Negative 1 is also defined in that same region. So we're still sticking with this top one. 6 times negative 1 minus 1. is negative 6 minus 1, or negative 7. Finally, f of 8.5. 8.5 is greater than or equal to 7, which means that f of 8.5 is 1/12. No math there needed, really. Okay, now we're going to look at a problem that's more of an example. Because of the pressure to complete a project, an employer offers its employees $12 for each hour of work, regular time, and triple time for each hour of overtime. So the first 35 hours are regular time, and everything after that is overtime. What we're saying is that we have a first 35 hours with a different case than if we have the hours after 35. So the first 35 hours, he is getting paid $12 per hour, 12 times h. This says the function is the project is a function of h, and h is defined as the number of hours worked, and he's getting paid $12 for each hour of regular time. So first 30 hours, we can also call that regular time. Then we have overtime. And overtime is the hours after 35. Now, that is going to be equal to an amount times a time. And that's important. You can actually model it off of the one above. We have an amount times the time. Well, what's the amount? The amount is triple time for each hour of overtime. So triple time would not be 12, it would be $36. That's the amount. The time in terms of h, this is a little bit tricky. Let's think about if we worked 13 hours. If we work 13 hours, we want to take that 13 and subtract it from, there's not 13 hours, let's say we work 36 hours. 36 hours would mean 1 hour of overtime. 37 hours would mean 2 hours of overtime. We want to take that h and subtract the 35 to figure out the amount of overtime, or the time of overtime. So those are the two kind of expressions there. Now, furthermore, we have one more little thing to consider with this whole overtime thing. I is income. So we're going to define the income now as it is $12 per hour whenever h is in between 0 and 35. Now, when h is greater than 35, we then start to do this other equation. I know this drives you nuts, but I'm going to shift this off to the right here, because there is something we have not yet considered. There is no real link between the top and the bottom. So if I say that he makes 36 times h minus 35, that means that if you work 35 hours, you make $0. That doesn't make sense. This, right now, the way we've written it, only accounts for the overtime. It doesn't account for the amount you made originally. So if we're going to say that this is really an amount made, I'm going to kind of come back up here, and we have to add, basically would be the 35 hours we worked regularly. So I have to add the 35 times the h of 12, or times 12 hours. Or sorry, $12 times 35 hours, other way around. 35 times 12 is $420. What that means is we make $420 once we work 35 hours. Plus 420. Okay, I want to stick on this for just a second, because we have to look at what's happening here. When the income is in between 0 and 35, we're going to start increasing by this amount. Once we hit 35, we make $420. When we make $420, that gets banked because we now switch our focus and looks here. And then we add on to the 420. But what we're adding on is actually $36 times that, not $12 times that. It's more, it's triple time. So that's the basis of this equation. When we're greater than 35 hours, we already have $420, and we're making this much more. So use this function to compute the weekly income if the employee works 35 hours. So let's do this. 35 hours h equals 35 means that we're going to take this, plug it into the top one. 12 times 35 is $420. That makes sense. H equals 42. We're going to take that and plug it into the bottom one. We have 36 times 42 minus 35 plus 420. The way that that equation is operating is it's saying we actually work 7 hours of overtime, 36 times 7, plus the original $420 of having worked 35 hours of regular time. 7 times 36 plus 420 is $672. Finally, if you're working H equals $48, 36 times 48 minus 35 plus 420 gives us 888. Use the function defined by the graph to find each of the following. Okay, those directions should have kicked over, so sorry about that. Hopefully on your handout it's correct. Here's a piecewise function graph. This one's a little nuts. You got 4 pieces. The way I look at it, you have 2 linear pieces, and we have 2 pieces that don't look quite linear. This one isn't quite linear. G of negative 8 means that on that function, when you see negative 8 for the x right here, what's the y? That's negative 7. G of 0 is negative 2. And G of 4, well, G of 4 is 0, so that's G of 0, and then G of 0 is negative 2. Okay, then we have 1/2 f of 8. That's a typo. Can't believe that's stuck in here already. There is no f. So I would say there's nothing there, but then let's change that to 1/2 g of 8. G of 8 back up here is, let's see, 8 down to negative 3. So G of 8 is negative 3, so that's just 1/2 negative 3, which is negative 3/2. Then it says, for what value of x is G of x equal to 0? We've done graphical analysis before. When G of x is 0, that's like saying y is 0. This is another way of saying where are the roots, or the x-intercepts, or the zeros. The zeros of this function are here, here, and here. Those are negative 2, positive 2, and positive 4. So negative 2, 2, and 4. And then what is the equation for the piece whose domain is negative 8 to negative 4? Negative 8 to negative 4, that is this piece. 2 points determine a line. This is the ordered pair, negative 8, negative 7, and this is the ordered pair, negative 4, negative 6. So if I want to take these 2 points that I can see from that line, come right back down here. Oops. Sorry, I'm trying to move these down here quickly. And let's do a line on this. I know the slope is equal to negative 7 minus a negative 6 over negative 8 minus a negative 4, or negative 1 over negative 4, or positive 1/4. Since the line passes through either of these 2 points, I can do I can do y minus one of them, so y minus a negative 6 is equal to 1/4 x minus a negative 4. Since it's a function, we're going to express it in function notation, which means slope-intercept form. Y plus 6 is equal to 1/4 x plus 1, or y is equal to 1/4 x minus 5. That would be the equation for that particular piece. And we're done.